Get ready to blast off into the incredible world of brain-computer interfaces. Neurocareers doing the impossible is taking you on a journey to meet the fearless pioneers pushing the boundaries of what's possible. In this special series, we'll be shining a spotlight on the nominees and winners of the International BCI Award, one of the biggest and most prestigious awards in the BCI world. You'll hear from BCI professionals as they share their revolutionary work and get a behind the scenes sneak peek at what it takes to be a winner. So, buckle up, grab a snack, and get ready to be amazed as we explore the impossible becoming a reality in the world of BCIs. But before we blast off, I want to give a big thanks to the co-host of this BCI Award edition on our podcast, Dr. Christoph Guger and GTech Medical Engineering. When I was a faculty member at the University of Cincinnati and Cincinnati Children's Hospital Medical Center, my team and I did some pretty amazing stuff for patients needing epilepsy surgery. We would put special sensors, also called grids, directly on their brain to prepare for surgery and create maps of their brain in a much faster and safer way than is usually done. It's called high gamma mapping, and it lets us figure out in just a few minutes the essential parts of the brain that need to be spared during surgery. Can you imagine? You can create a map of language, motor, and even math processing in no time. It was the first time this innovative technology was used at Cincinnati Children's Hospital Medical Center. When I moved to Florida, I established the first functional brain mapping and BCI program at Florida Hospital. I continue to use high gamma mapping to help epilepsy patients avoid losing their ability to speak or move after surgery. But even cooler than that, I created brain-computer interface studies that let patients control things with their brain in real time. Our patients could even spell words with incredible speed by just using their brains. No hands involved. I also discovered that brain-computer interfaces could help patients move their chronically impaired hands or legs years after a stroke when not much else could help them. So I started working with the faculty from Advent Health University to help these patients restore their ability to use their hands. I received special training for it, and it's still mind blowing how cool it is. My favorite part of what I do is teaching. At my established Institute of Neuro Approaches, I've integrated all my experience and knowledge into a unique course on brain-computer interfaces. With graduate neurobiology students, we started with theory, and then I gave them the BCI equipment so they could have hands-on experience working with BCIs. It significantly improved the way students learn, and they absolutely love this practical part of learning how to use neurotechnology. And all of this was made possible thanks to GTech's awesome brain-computer interface technology. They have everything from high-tech up to 1024-channel EEG systems to wearables, tools for neurorehabilitation, such as the medical grade system recoveries and educational kits with unicorn hybrid plug for learning how to work with BCI technology. But the most important part is their support and care. I have enjoyed working and collaborating with Dr. Christoph Guger and GTEC employees for over 15 years, and I hope for many more successful years ahead. So, if you are interested in GTEC's brain computer interfaces and neurotechnologies, check out their website at gtech.at. It's worth it. And keep in mind, I do not receive any financial support from GTEC and share my honest opinion supported by many years of experience working with their equipment. Dear listeners, welcome to another episode of the Neurocareers Doing the Impossible BCI Award podcast series. Today, we are diving into an inspiring project working naturally after spinal cord injury using a brain-spine interface that has shattered the boundaries of spinal cord injuries, offering a new way to mobility and independence. Imagine a world where spinal cord injuries no longer result in permanent paralysis. Come with us as we delve into a pioneering project that has created a digital bridge between the brain and spinal cord, allowing a person with chronic tetraplegia to stand, walk, and move naturally. The groundbreaking brain-spine interface, BSI, includes implanted systems that link cortical signals directly to epidural electrical stimulation. This targets specific spinal cord regions crucial for walking. Published in Nature in 2023, this exceptional project restores movement control and enhances neurological recovery through BSI-powered neurorehabilitation. Our guest today, Dr. Henri Lorach from Neurox Institute at EPFL, Switzerland, was instrumental in this groundbreaking project. As a senior researcher and head of the brain-spine interface unit, Dr. Lorach brings a wealth of experience and insight to this remarkable work. Join us as we delve into the details of this project and explore Dr. Lorach's expertise in the field of neurotechnologies. Moreover, Dr. Lorach is a key contributor to transformative research and a member of the jury for the BCI Award 2023. With his wealth of experience, he will provide invaluable insights into what the jury looks for in submitted projects and offer advice on crafting a successful project submission. Tune in to gain a deeper understanding of the project that claimed first place in the BCI Award Competition 2022. Learn from Dr. Lorach's expertise and embark on a journey into the future of neurotechnology. Hello, Dr. Lorach. It's a great pleasure to have you today on our podcast. Thank you so much for joining us. Can you please introduce yourself and tell our listeners where you are joining us from what part of the world?
Thank you very much, Milena. Thank you for the invitation and the opportunity to join this podcast. I'm located in Lausanne, Switzerland, where we have our clinical laboratory and perform those experiments and those technological breakthrough. Here we are going to talk about this brain-spine interface where we use cortical data, invasive neurotechnologies to record cortical data and drive a spinal cord stimulation after a spinal cord injury.
Thank you so much. And can you introduce briefly your institution? Because people are listening to us at different parts of the world and they may not know anything about this place. So it would be good to introduce it.
Yes, exactly. So My name is Henri Lorach, and I work at Neurorester, which is it's an institute that gathers a team from the University Hospital of Lausanne, the CHUV, and École Polytechnique Fédérale of Lausanne, EPFL, in Switzerland. So we gather teams from clinicians, from engineers, and biomedical engineers, physiotherapists that work together to tackle disease that affect neurological function.
Thank you so much. So do I understand correctly that this research, it happens at different institutions in Switzerland? Yes?
That is correct. We gather forces from University of Lausanne, École Polytechnique Fédérale of Lausanne, and we have some preclinical research also located in Fribourg, everything in Switzerland, but teams that are within this institute to tackle neurological function.
Mm-hmm. Thank you so much. And can you tell a little bit about your path into this field, into neurotechnologies? How did you come to this place when you started working on creating the bridge between the brain and the spinal cord?
So I was actually trained first as an engineer in France at École Polytechnique, and I specialized in neuroscience and neurotechnologies, and I started my PhD in neurotechnology working on prosthetic vision. So basically, I did not work on the motor system, but on sensory prosthetics. And I worked on the retina and how you can stimulate the retina after you lose photoreceptors to recover some visual sensation and recover vision after losing it due to different types of disease, either genetic disease or traumatic disease that affects the retina. So I did my PhD in France, in Paris, with Serge Picot, working on retinal physiology and retinal prosthetics. And then I moved to the US, to Stanford University, to develop a new type of retinal implants, photovoltaic implants that convert directly light into electricity. So that use the natural optics of the eye to convert light into electrical stimulations and restore prosthetic vision.
And how did you make a choice to move from this very exciting field of study, very promising field, and to start working with the motor systems?
Yes, it's a shift, but it is very complementary. So the principles to stimulate electrically the neuronal system, the nervous system, is actually common between retinal prosthetics, motor prosthetics, or sensory motor prosthetics. So the principles of stimulating neurons, modeling electric field, and how to optimize stimulation, it's common to all these different fields. What I learned from sensory neuroprosthetics is, of course, applicable to sensory motor prosthetics, and now, in particular, working on the motor system, we have those principles that translate to the other fields. So I don't feel like I switch completely gears. It's a complementary experience, and probably it enables to have a different view, a different angle into a new project.
And what did you add to your previous skills that helped you with this new project on control motor rehabilitation?
So I switched topic, but also I switched system because I was working on preclinical modeling, preclinical research with rodents. So doing animal work, surgeries, electrophysiology on animals. And here, as I joined this project, I worked on the clinical aspects. So I think being able to go from basic research to the clinical research gives a broad view of what you can push and the insights you can gain in preclinical research to push in parallel clinical and more basic science.
Mm-hmm. Thank you. Now let's get already to the project itself. Maybe you can just give a brief synopsis of it, and then we will go into more and more detail.
So in this project, in this paper, we describe the development and the clinical use of a digital bridge, which converts decoding intention from the motor cortex into stimulation of the spinal cord and motor activity elicited through stimulation of the spinal cord to restore voluntary movements after paralysis. So this project, this study, shows the technical advance and the conceptual advance to really reconnect the brain and the muscles below a spinal cord injury lesion. So here we describe the journey of one participant, Mr. Oskam, who was in a bike accident 12 years ago. He got a cervical injury, and after 10 years of paralysis, being bound to the wheelchair, he joined the first clinical trial, which we call STIMO, where he was implanted with a spinal cord stimulation system. This was in 2017 in the first study. And in this study, we looked at how we can restore motor activity using this spinal cord stimulation. So we place an array of 16 electrodes over the dorsal aspect of the spinal cord, and each of these electrodes can trigger specific muscle activity in the legs. And by creating a pattern of stimulation, we can mimic the pattern of muscle activity that is required for walking. And with this technology, at the time, we were able to restore some locomotor activity, so restore walking in a pre-programmed way. So we were able to pre-program a stimulation pattern that would make the patient stand and walk at a given rhythm. What we did in this new study, the participant in 2021 got a second implant over the sensory motor cortex, where we could this time record his cortical activity while attempting the movement, which means that instead of being pre-programmed and triggered externally, now the stimulation could be controlled by his motor intention that we were able to record from the brain. And so the device that we used is called the WIMAGINE device that was developed by collaborators in Grenoble, in France. It's a 64-channel electrocorticographic array, which sits at the surface of the dura mater. So we replace a piece of skull by this device that records cortical activity between 1 Hertz and 300 Hertz at 600 Hertz sampling rate over these 64 channels, and where we can train a decoder to interpret and to decode the intentions to move different joints. And so we connected the decoding, the BCI decoding that we got from this device to the stimulation patterns that we had previously explored.
Yeah, thank you so much. And it's so interesting that the same participant participated in the first clinical trial you had and in the second clinical trial. What motivated him to participate in the second trial after the first was over?
So first, I should specify that this second clinical trial was only open to participants who had already been implanted with a spinal cord stimulator. It was one of the inclusion criteria. The reason why is that we wanted the participant had reached a plateau of recovery using stimulation alone, meaning that he had pushed his rehabilitation using the stimulation as much as possible. And we wanted to see the additional benefits of bringing in the brain controlled aspect of the stimulation. And that's why this study was opened for participants who had previously been implanted with a spinal cord stimulation system. And for him, he felt like he could still progress, and he felt like this addition would be a game changer, and that's why he participated to the study.
Were any concerns about implants into the brain, basically, which differs from the stimulator that he had before? Did it raise any concerns? How did he react at this possibility of?
Yes, so the spinal cord stimulator system is also implanted. It's an invasive system. This second surgery targeted his brain, but as I said, the device stays on top of the dura mater, which means that we don't go inside the brain. We keep this natural protective layer, which is the dura, and we record at the surface of it, which reduces some of the risks, such as a leak of cerebrospinal fluid or infection. But that said, yes, of course, there were concerns about implanting a device, risks of infection, risks of bleeding, risks related to the anesthesia. But those risks are well known and well controlled. And that's why when we submitted this clinical trial, we performed this risk assessment and obtained clearance from the Swiss authorities to perform the study.
Okay. Now let's get a little bit deeper and deeper into the project itself. So, first of all, what was the main goal of this project? What did you want to achieve?
So we had two main objectives. The first one was to show that we would be able to decode intentions and drive spinal cord stimulation and restore this prosthetic control. This was the clear goal. We knew, we expected to be able to restore one joint, maybe two joints. And here we studied how many degrees of freedom we were able to restore with the system. We went up to 6 different degrees of freedom, 3 movements on both legs, which was one of the questions we had. How much degrees of freedom would we be able to restore? And the second objective, the second hypothesis, was that using brain-controlled stimulation, we could even enhance the neurological recovery. And that's what we observed after 40 sessions of training using the system. The patient recovered neurological function of the different joints that we trained with him. So these were the two main challenges, the two main hypotheses that we tested in one participant.
Mm-hmm. Thank you so much. And now how you were testing also step by step. So first of all, of course, you needed to implant those devices, yes, bilaterally over the sensory motor cortex. What procedures did you use to localize, where exactly should those devices be implanted?
Yeah, so anatomically, we know where is the sensory motor cortex. Of course, it's quite preserved between individuals. So we had the first anatomical guess about the localization of the brain implants. We performed additionally magnetoencephalography during attempted movements in order to verify that the patient was still able to visualize those movements and was able to elicit significant activity over the motor area that we can pick up and that we can actually decode. So this step of preoperative mapping comforted us in the localization, the precise localization of the implants. Over the spinal cord, these steps were performed a few years before when the patient received the implant initially. We know also the anatomical localization of the roots, the spinal roots that innervate the different segments of the spinal cord related to different muscles. So we know between the lumbar segments and the sacral segments where the implant should be placed in order to selectively activate the different muscle groups. So we had this preoperative planning for both stimulation and recording over the cortex. And that's what enabled us to precisely place the devices. So after the implantation, after the surgeries, we performed calibration of the stimulation and of the decoding devices. So we asked the participants to visualize the different movements, hip flexion, knee extension, ankle flexion, and we looked at the cortical activity patterns that were correlated to each movement. And that's how we identified the different frequency bands, the different electrode localization that encoded most of the information related to each movement. For the stimulation, we also mapped the effect of stimulation of the different electrodes, and by a systematic mapping, we were able to find which stimulation patterns were the most selective for those hip flexions, knee extensions, or ankle flexion, so that we could map a brain state, brain probability pattern to a stimulation pattern.
Thank you so much. And what about the signal that you were recording? Because in intracranial studies, or when the signal is being recorded directly from the brain, even in this type of recording, there are questions of the stability of the signal. Yes, whether it changes from day to day and over time. I know that you showed actually beautiful stability of the signal, which you described in the paper. Can you comment more on that? What did you observe, and how do you explain this stability of the signal?
Yes, so you're right. One of the big questions is, can we use the system for an extended period of time? How does the system behave over time? And what we observed by looking at the power spectrum in the different frequency bands over time, is that in the first 30 days after implantation, we see a change in the amplitude of the signals. The signals tend to increase over those first 30 days. And after 30 days, we see a stabilization and a very slow downward slope in the amplitude of the signals. We quantified this slope, and we showed that basically the signals could remain stable over several years. So how we interpret this is that the device is epidural. There is an initial reaction of the tissue within the first 30 days. There is fluid accumulating at the surface. There may be some tissue gliosis that could happen within the first 30 days. And after this stabilization period, the distance between the cortical surface and the electrodes is stable, and the amplitude of the signal is stable over time.
I'm very curious about the care of those electrodes. Is there a need to clean them? How often they need to be cleaned to the surface area? How does it look like in everyday person's life?
So maybe you have the vision of somebody with a connector on the head. This is a case for UTA arrays, for example, intracortical electrodes, where, yes, patients need to be connected physically and to have a transcutaneous connector that goes through the skin. And there, of course, you need some care to avoid infection and to maintain the stability over time. In our case, the device is wireless, meaning that once it's implanted, you have an antenna under the skin. So the skin is sutured over the implant. And this antenna enables powering and data transmission wirelessly. So typically the patient would wear a little headset with an antenna that would wirelessly transmit the data and power to the implant. So once it's implanted, we don't need to clean anything. We don't need to maintain. The system is invisible once it's implanted.
Yeah, that is certainly a very big advantage, especially giving a person possibility to use it autonomously without need to come to the lab, and many things can be done directly at home without many additional procedures.
Mm.
And now let's look at the frequencies in the signal that you were using for your data analysis. Can you maybe comment a little bit on that? What frequencies were giving the most information that you were using?
Mhm.
And also the type of time frequency analysis that you were performing to analyze the signal?
Yes, it's a very good question. So in our models, typically, we would input all the different frequencies from 2 hertz up to 200 hertz and let the algorithm learn the weights of each frequency at each electrode position. So we saw that we had contributions of low frequency, of beta frequency, gamma frequencies, basically over a wide range of frequencies depending on the electrode position and depending on the state. So we wanted to decode rest versus hip flexion versus knee extension versus ankle flexion. And what we saw is that this combination of spatial, spectral, and temporal information was essential to discriminate the different states. So to answer your question, we would say that all the frequencies between 2 hertz to 200 hertz were included in our analysis and in our decoding.
Mm-hmm. Yep, that makes sense. And now about the stages of this project. So from the article you published, I saw that there were several stages where the participants started with performing a basic movement on a flat surface. Then you were moving into already more complex surfaces. So can you tell about this progression and how did it occur also from technical perspective?
Yes, very interesting. So we started initially with simple movements, individual movements, where we able to trigger right hip flexion in a controlled environment, first sitting in a wheelchair. We started to use the system, even just controlling an avatar. So the very first step was the patient controlling a virtual reality environment, an avatar, and trying to trigger different movements of the avatar himself. Once we validated this step, we connected this decoding to stimulation over 1 degree of freedom, let's say, hip flexion, and we showed how this brain control stimulation enhance his contraction and his step height and his movements. So these first steps, yes, we had a very bulky setup in the sense we had an external computer, desktop computer for decoding, for stimulation, many screens to be able to visualize everything. And once we understood the first models, once we performed the first link between the brain and spine, then we integrated the system in a portable environment. And it was important to be able to train outside and to train in different environments. And what we showed is, thanks to this technological development, this system integration, we were able to go outside and to train new models that would perform in very challenging conditions, such as walking over steps, stairs, or in outdoor environments. So yeah, it's a combination of training with the patient, improving the system, improving the system packaging, capacity, battery life, that enabled us to go outside and to improve the quality of his gait in challenging situations.
Mm-hmm. Can you describe the final look of the system? I know that the patient had like a walker, and there was an area in the walker that was used for keeping certain equipment. So the final product, how all the system looked like.
Yes, so it's illustrated in one of the figures of the paper, but to describe it to you, it's a walker, so four-wheel walker that the patient can use to support some of his weight, to keep his balance, where we have added a box containing the amplifiers, the communication system, the laptop that controls the stimulation, and the patient basically can put on his headset, the communication headset that I described, in order to communicate with the implant. He can position the communicator with his spinal cord stimulation system. He then opens the computer, starts his program. Everything starts sequentially. He has freedom to change some of the amplitudes, stimulation amplitudes, and he can start stimulation. And so once he has set up the system, initialized the system, he has triggered this link between his brain and his cord, and he can start using the system independent way.
Mm-hmm. And how long does it take to initiate all this process to start working?
Typically, starting the Windows computer is what takes most of the time. So we still rely on off-the-shelf equipment, off-the-shelf laptop. So it's about 3 to 5 minutes to set up the system, which is okay, but can still be seen as a barrier to be able to use it every condition. So those 5 minutes is what we are currently working to reduce really, and to have a instantaneous connection between all the different pieces of equipment. So that's the next breakthrough will be technological, in the sense that everything should be integrated in the phone, for example, and everything should start within 5 to 10 seconds.
What was the degree of independence of the participant at the end of the trial when you already troubleshooted everything and it was like the final product?
So the degree of independence in operating the system?
Yes.
So
yeah.
the patient is now the expert.
Okay.
Now, yes, the patient was really part of the team also during the development. He had a lot of very insightful feedback. And so now the patient knows all the little tricks of the system, is able to debug the system if needed. So he's fully independent in using the system. Mm-hmm. That said, yes, he's always proposing new iteration, and we keep collaborating with him.
So it's so important to collaborate not only within the team, but with the participant who can provide so many insights.
Of course.
I'm very curious to how long the participant was able to walk in a given period of time, because obviously he might get tired. There are certain time constraints. So what are those?
So there are also the technical constraints and the physical constraints. So in terms of technical, everything is embedded, and we have a battery life of about 2 hours. So the system can be used continuously for about 2 hours. Physically, it's challenging to walk for 2 hours. So we would have sessions of, let's say, 20, 30 minutes of continuous walking, then a little break, then 30 more minutes. But for now, the constraints are more physically for the patient to be able to maintain this duration.
And you also mentioned some problems with balance. Yes, and that's why the walker is also very helpful. What are the causes of this imbalance, and how this maybe in the future might be corrected with the additional maybe technological developments?
Yeah, it's a very good question. So, because walking involves not only the legs, but a lot of trunk balance, trunk support, that in this participant and in many injuries is actually impaired also with cervical lesions. You lose control of the trunk muscles. When you have a lesion that is lower, that might be thoracic, you have some patients who keep some trunk stability, but it's not the case in all the patients. So often the abdominal, the dorsal belt is also impaired. And so our stimulator, as it was placed currently, is only targeting the leg muscles. What we need for the next generation is to also cover the trunk muscles. And this, in another clinical trial, we explored how we can actually recruit the muscles of the trunk and bring stability over the upper body during this stimulation. And it's this combination that could help with the balance. So in the current study, the current state, we rely on this walker or crutches that the patient can use to stabilize himself.
Yes, so of course, I'm looking forward already learning about your ongoing projects, and hopefully this problem will be solved in the future. And now I would like to talk a little bit more about the next stage of your project, which was relevant to neurorehabilitation. So, can you talk about that? So, it's not only that project or device allowed a person to walk, but also helped with the neurorehabilitation. So, can you talk about that?
Yes. So as we said earlier, the two hypotheses is this prosthetic motor control, but also neurorehabilitation using the system. So this, depending on the severity of the lesion, we expect a different effect. In mild lesions or incomplete lesion, we expect a very high rehabilitation effect. And of course, in very severe lesion, when there are very few fibers left crossing the lesion, we don't expect as much plasticity and as much rehabilitation. So depending on the patient and his level of injury, his severity of injury, we expect different type of neurorehabilitation. With this participant who had an incomplete injury, we observed this rehabilitation effect on muscles that were basically at a plateau level for many years, even using the stimulation alone. So we really observed this rehabilitation effect using this brain-controlled stimulation because he could synchronize his intention and he found a way back to his muscles that he had lost for so long. And so the hypothesis is that the spare fibers are able to make new connections with the motor neurons that are recruited through stimulation. And this was possible because of remaining fibers and an incomplete lesion. In motor complete lesions, we expect less of this phenomenon to occur.
So, how was the perception and the attitude of the participant changing over time, as you know, starting with just basic steps, going to more complex surfaces, then improving the effect of neurorehabilitation? What was his experience with this?
So the patient had a lot of fun to work with us, and he became more picky and more picky. Meaning that, initially we didn't know what were the limits of the system in terms of latency, in terms of decoding accuracy. So we started with simple tasks, and as we learned and we learned, he learned too to adapt to the stimulation, and became more picky about the timing of the stimulation, the amplitude of the stimulation. And that's how he really contributed a lot to the project by being giving good feedback on the latencies, the timings, and how to improve the system. So he was motivated all the time and really giving us input in the everyday situation. I think for him it was not only was happy to gain these functions, but to participate in this journey and to be a contributor. I think was a huge motivation for him.
And what was for you the most unexpected thing in this journey during this clinical trial?
The most unexpected thing for me was that everything happened as we expected. Yes, we had planned for many different situations, and overall there were no big surprises. I would say the most incredible was that in a few minutes, the first time we plugged in the system, using only the avatar and the virtual reality environment, in just 5 or 6 repetitions of the movements, the decoder could learn the features and be able to control the avatar in such a short amount of time. So without specific mental strategy, or we just as a patient think about flexing your hip, and this natural strategy basically succeeded in the first attempt. So that was a big surprise.
Yeah, that is amazing how natural it occurs without thinking that, oh, I need to, like initial studies, yes, when the person needs to think how he is flexing the right hand versus left hand to move forward, to move back. This was happening very naturally. Just thinking about the movement itself, for example, for hip
Yeah, the strategy was really always focused on the joints and on a specific muscle activation, which is slightly different to other BCI's systems, where you may think in direction or you may think in a cursor position and have a mental strategy to achieve this switch. Here we really gave the instruction to think about a muscle, like think about contracting a given muscle. And that's how we got this decoding performance.
Mm-hmm. What was the biggest challenge in this project and how did you solve it?
So the biggest challenge was to get regulatory approval for the project. But this is a side note. Yes, the biggest challenge was technological challenge, putting all the pieces together, making sure that everything fitted with the shortest latency possible, that the brain implant was positioned exactly where we wanted, that the signal to noise ratio was high enough. So it was not one challenge, it was everything had to work perfectly to get this performance.
And what technological advances were maybe inspiring or motivating you in your search for the best decoding approaches or feature selection? Now there is a lot of innovation and development that is going in the field of machine learning. Yes, we have, of course, everybody is talking about AI. So is there anything that is happening right now helped you in your project and maybe motivated you?
Yes, I would say for this first step, we relied on more classical machine learning algorithms that we now are shifting to really exploit the AI methods to be able to generalize decoding to new tasks, for example, to new patients. I think in the future, that will be the biggest challenge to be able to reduce as much as possible the calibration time. We can harvest all the information we have from previous implants, from different recording modalities, invasive, non-invasive, and combine all this knowledge in a brain language model. And that's what we are working on currently to be able to shorten as possible the training times, increase the number of degrees of freedom that we can control, and use more sophisticated in the sense that we, instead of using linear regressions, we will use few transformers layer, but always in the sense that we can harvest information from other patients and from other tasks in these models, in these networks.
What type of patients do you think you can generalize the results of this study? Who would be the first possible users of this type of system?
So the clear target are first patients with spinal cord injury, so thoracic or cervical spinal cord injury, where the only requirement is that the spinal cord below the lesion at the lumbar level is intact, because we need to stimulate those motor pools. We need a brain that is still functional, so motor cortex, where we can still decode information. So for this, most of the spinal cord injury are actually applicable. We are starting to work to use the same principle to restore arm and hand function. So for the upper limb, we can stimulate the cervical region of the spinal cord to reactivate the different muscles of the arm and restore voluntary control of the arm after tetraplegia. So this is also the next target population, patient with cervical injury to restore upper limb function. And we are looking into specific stroke models. So patients where the stroke would affect the motor cortex partially, or subcortical stroke where there would still be some decodable motor inputs, and we can use these decoded intention to drive spinal cord stimulation where the spinal cord is completely intact, and apply this brain-spine interface also in those stroke participants.
Yeah, and in stroke participants, obviously, for motor rehabilitation, it also can be very important.
Very important, yes. So always the challenge is to be able to treat as early as possible before spasticity occurs that could then hinder the movements. The optimal time point to implant the system and to start the rehabilitation is still a big question. So try to implement the brain-spine interface in a very early spinal cord injury or very early stage stroke will be telling us also the potential of rehabilitation in the early stage.
Mm-hmm. So what were the main results of your study, if you could summarize them? And of course, in parallel to your main goals, how did you achieve your goals?
So again, the two main questions were how many degrees of freedom we can restore using this digital bridge. We showed that we could control up to 6 different movements of the leg and restore natural walking in one participant. And the second question was about rehabilitation. Could we gain additional neurological recovery using the brain-controlled spinal cord stimulation compared to spinal cord stimulation alone? And here we showed improvement in the neurological scores and functional improvements in almost all the different measures that we tested with this participant when we compared post-rehabilitation with pre-implantation.
And what became possible with this project that wasn't possible before you completed it?
Really, this project opened the concept of a clinical brain-spine interface where the muscles of the patient itself are the actuator of the BCI, and we can really reconnect the brain intention with the own muscles of the patient. So this had been done a few years ago using FES, functional electrical stimulation, and neurocare and published. But here we use spinal cord stimulation and recording of the brain that are chronically and clinically available, which means that it's a realistic therapy that could be disseminated to many participants. And that's what we believe is the breakthrough, is to have this concept that is clinically viable minimally invasive, and translatable to many, many patients.
How do you see this system, let's say, in 50, 60 years from now?
I think we can be very hopeful that all the external components can be miniaturized, and the algorithms can be run on a smartphone or in the cloud, and that everything is embedded in one little switch device or an app that the patient could start himself and have the system on for the entire day. And basically have this new way to control his muscles that is not his initial and natural way, but that is his new way to control his body, where he would adapt, and the algorithm itself would also adapt. Like this co-adaptation would enable a continuous use, and that the patient ends up finding natural this new modality of controlling his muscles. And we can think, yes, that in 50 years, patient will get those implants in the brain and the spinal cord and be able to, if not walk naturally or run naturally, but maybe find their independence back in a seamless way.
And what technological developments do you think are needed to get to that point, to have this miniature device that easily can be used and contains everything that is needed to control the device?
To be honest, the technological developments are already there. We need the investment and the money to make it concretely in one device. So it's about development cost, integration engineering that are today even possible, but that need significant investment to be able to occur.
And of course, I wish your device all possible success, all possible finding, so that it could start helping many, many people. And you published this study in Nature. And because we have many people listening to our podcast who will be publishing, who don't have experience with Nature publication, what is the difference between publishing and preparing the manuscript for Nature publication versus other journals?
I don't think there are many differences, actually. I think you have the results is what makes your paper publishable in a journal or another. But yes, we try to design our paper as clearly as possible, to explain the results as clearly as possible, and then we submitted it to Nature. But of course, there are many other publications, many other great journals, and I think what was important for us is to make the message clear, the concept, that we reconnect brain intention with the muscles after spinal cord injury, and to explain the results as clearly as possible. But we would have done the same in any other journal.
Yeah. Thank you. Yes, it's really very clear, very nicely written. I advise our listeners to definitely read about the study. And I like how you called this link between the brain and spinal cord a bridge. Yes, so the bridge between, it's very intuitive because you immediately imagine how it's all connected. Thank you so much for this explanation. And now I would like to ask you a couple of questions about the career in neurotechnology. You already talked about your pathway from retinal implants into working with this device motor system. What do you think are the main skills that the person needs to have to be able to do this type of work that you are doing?
Yes, it's a very good question and hard to answer, because this work, of course, combines contributions from many, many people who are all specialized in different aspects, in software engineering, in hardware engineering, physiotherapy, clinical scientists, data scientists, regulatory experts. So the field of neurotechnology itself is very broad and requires, let's say, people that are specialized in many different aspects. It's hard to be specialist in all those fields. But I know that many students now turn to machine learning and to AI algorithm. I think it is very important to know the techniques and what it can do. But most important is to make things happen and gather the data and collect the data and to implement, let's say, a clinical trial like that takes much more than just analyze data. So just as maybe a message to people who focus only on data processing and on decoding, I think it's good to also open the perspective to really experimental science, to how the data is collected, how it is designed, how to design a clinical trial, how to make sure that you actually get the data you need to be able to train all your models and to perform all the fancy AI that you want. So I would say try to be balanced in the skills you get. Technical, machine learning, very important, but stay also open to the experimental parts.
Yeah, thank you so much. And actually, this is one of the questions that students ask. So, how much they should really become a specialist in one field, and then how much they should learn other things? What is that ratio? How much should they specialize in other areas rather than their immediate work, the skill that
interest?
Yeah.
Yes, it's. I think that anyway, whatever you learn at school, or you will completely forget and learn for each project what you need to learn. So stay flexible. It's good to arrive with a set of tools, a toolbox that you can implement. So being specialized in data analysis, signal processing, at least to have a good basis on this is very important. Biophysics, physics, very important in all the neurotechnologies. Yes, just stay open to everybody can teach you something in a project. So you learn from everybody, from the different team members who are all specialized in something. So you just need to stay open.
Yes, and of course, be open to communication, to collaboration. That is the key. So it's very important. And now I would like to talk about the BCI Award project submission. Of course, your project received the first place in 2022, and now you are a jury member in the BCI Award 2023. So, from both of those perspectives, what are your maybe suggestions to people who are planning on submitting their projects for BCI Award? What would you emphasize? What would be the most important points?
So I think the deadline is coming pretty soon. So
Yes.
not much time left to change everything and to write a new paper. But and also as a jury member, I did not officially receive any instruction. So on this part, I cannot really describe you the evaluation process, but it's very detailed on the website. So the key aspects are to have a system or a concept, a BCI concept that is realistic, that is applicable, that can help many people, and that should focus on the user needs. And I think for me, it's very important to always start from what the patient, what the BCI user really needs. And it can be a very simple project, it can be a very simple algorithm, but if you really match the use case and the need of the patient or the participant, it can be very powerful. So I would say whatever the algorithm type, whatever the BCI strategy that you choose, really try to focus it on the need, on the purpose, and it can be very successful.
Thank you so much. Would you provide any advice to those people who are just getting into the field of neuroscience, neurotechnology, and of course, who are interested in participating in studies like this? How can they find potential possibilities to participate, make some impact?
Yes, so my recommendation is always to get as much hands-on experience as you can, do as many internships as you can, build up your technical skills, and reach out to people. Don't hesitate to send emails. People are usually very happy to discuss informally or to propose internships. So don't wait for open positions or to advertise position. Often when it's the case, it's already filled, or it's always better to reach out to researchers and to projects, read a lot of paper. And if you see one question, one topic that really motivates you, that's where you should focus your efforts and contact the people you need.
Great advice. Thank you. And one question that I ask all of our podcast guests, it's about doing the impossible, because our podcast is called Neurocareers, Doing the Impossible. What was the project in your career that might have seemed as impossible, but you eventually made it possible? And how did you do it? What would be your advice for making the impossible possible?
It's a hard question. I would say the strategy would be never to think that it is impossible in the first place. I think that you should always consider challenges, define what will be the bottlenecks, what will be the locks, the challenging points, and just address them one by one. If after that you still think that it's impossible, or you see some challenges that after really careful inspection you cannot resolve, maybe you have to redefine your strategy or shift slightly your angle. But I would say the best way is to never think it's impossible in the first place. So yeah, in my case, I think I had some challenging projects in all the different stages of my career. But it's always about defining what will be the challenge, and how to overcome each small steps. Not seeing the big picture, or not being overwhelmed by the extent of everything that has to be accomplished, but see small challenges one at a time.
Thank you so much. That's great advice. I absolutely agree with it. And as we are nearing the end of our podcast, would you like to say anything to our listeners, share anything before we end our podcast?
I just want to thank you for the invitation again. Thank the listener, and thank also the BCI Award and BCI organizers that really push forward the field. And it's really a pleasure to be part of this community. Yeah, thank you.
Thank you so much. It's been a great pleasure. I'm sure our listeners will enjoy this podcast very, very much. And I wish you all possible success and in your career journey and in your amazing projects that you are doing with an amazing team. Thank you. Are you a fearless pioneer in the world of brain-computer interfaces? Do you have an amazing project that's pushing the boundaries of what's possible? Then we want to hear from you. The International BCI Award is one of the biggest and most prestigious awards in the BCI world, and the deadline for submission is September 1st. But don't worry, you don't need a top notch budget or equipment to be a nominee or a winner. All it takes is a great idea and the determination to make the impossible possible. So, submit your project now at bci-award.com or find the link in our podcast notes and join us on this incredible journey to explore the world of BCIs. And make sure to listen to our upcoming BCI Award Neurocareers podcast series for tips and tricks on creating a successful submission. Who knows? You might be the next nominee or winner of the International BCI Award and proudly showcase your nomination on your resume to impress potential employers and establish a successful career in neurotechnologies. But don't stop there. If you're looking for more guidance on succeeding in neurocareers, book a free consultation with me, your podcast host, Dr. K, at the Institute of Neuro Approaches. So, what are you waiting for? Let's make the impossible possible together.